Jim Waugh is an American airline pilot who flies the North Atlantic for Pan American. Norman Todd is a British airline pilot who flies the North Atlantic for BOAC. In exactly 3 hours, both pilots will take off on their regular flights to London. What is the risk that Captain Waugh will collide with Captain Todd somewhere over the wide expanse of ocean? Jim Waugh has never met Norman Todd, although they've both been flying the North Atlantic for over 20 years. During that time, air traffic, like automobile traffic, has grown so much that it can't be handled satisfactorily at peak hours. The first part of the problem has to do with the way people travel. At this hour, almost no one wants to go in this direction, but everyone wants to go in this direction. Automobile traffic is subject to tidal flows, which peak in one way in the morning and in the opposite way at night. Airline traffic across the North Atlantic not only has daily peaks, but weekly peaks and yearly peaks. In early morning, at the end of the week, in summer, nearly everyone on this side of the Atlantic wants to get to the other side.
Morning.
Good morning.
Could I have the papers for 100?
Yes, we're expecting...
The second part of the air traffic problem has to do with the airplanes themselves. Jets operate most efficiently at certain high altitudes. Because of the influence of strong winds that may reach hundreds of miles per hour, they also operate efficiently only along certain flight paths. All the jet pilots try to get the best of the few official air corridors, an air corridor nearest to his ideal flight track. But there are only a few of these corridors available.
It should be very smooth.
And could we look at the plot on the track over there?
Yes, I have it right here. Now, the ATC has said that the tracks are north of this red line here, and we have you plotted here, out over New York, Stephenville, and over the ocean. It takes you over Shannon and down to London.
And this is the least time track that we're looking at.
That's the least time
right
track.
Here. Very good. Well, thanks very much, Chris.
I might mention that the Bushmills is off the air for about 5 hours this morning. It'll probably be back on by the time we get over there.
What's the fuel available then?
57, you have 59 available.
No, I think we'll take the 59 in that case. But what about the weather at the other end? We better make sure
Forecast
that.
will look fairly good. Here we are.
Rain as usual.
Sure.
Good for the garden. What's the reason for going north? That's the best time, is
The
it?
best time track actually is here over Stephenville, up to
Yeah.
55 at 40, and then down over Eagle Island.
That's all.
Good.
Good.
Right.
We'll take this.
And you're taking the normal taxi of...
Oh, yes, 1,000 kilos
1,000,
taxi.
right.
No. Thanks very much. Good.
Right. Bye-bye.
I'm very glad to know you all. I'd like to brief you on the flight to London. We're forecasting 6 hours and 11 minutes.
Captain Waugh passes on the weather and track information to his crew, some of whom, because of the tremendous number of crews, he may never even have met before.
Now, the galley girls will operate the emergency slides at the galley. Is that understood? Check. All right, our airplane is at gate 3. We'll see you on the airplane.
Clipper 100, clearance. Clipper 100, cleared as filed. Maintain flight level 240.
1 hour before takeoff, flight number and departure time are fed into the Federal Aviation Administration Control Center on Long Island, where ground controllers will use their radar to guide both captains on the first leg of their journey.
Clipper 100, taxi via Kilo, a right on Yankee, right on the outer taxiway, a left turn at taxiway Papa.
Speedbird 510, cleared to taxiway Kilo, right on Yankee, right on outer taxiway, left to Papa.
Release. Clear right.
Clear right.
Turbos, bleeds, fuel cistern, fuel heat.
Locks and covers. Circuit breakers, fuses. Fuel feed. Fuel on board.
Check is complete.
Central power, air conditioning pack.
Checklist complete. Takeoff briefing will be, you give me V1, VR, V2, plus 10.
Takeoff speed. Your V1 is 141, rotate at 157, 167 bucks.
With the traffic at its peak, the huge jets line up, one behind the other, burning up hundreds of pounds of precious fuel until finally they can take off.
Clipper 100, clear for takeoff, runway 13 right.
Takeoff power. Airspeed left.
Checks right.
80 knots.
Checks steady. V1. Rotate. V2.
Gear up.
Speedbird 510, cleared for takeoff, 13 right.
5%.
Set full power. Right, speed boarding both sides. 80 knots. Speedbird 510, contact Kennedy departure control now on 121.1.
Speedbird 510, that is Roger.
After the plane leaves the airport, it's picked up by the New York Air Route Traffic Control Center on radar scopes and tagged with an identifying marker called a shrimp boat. The radar echo from Captain Waugh's plane is tagged PA-100, and the echo from Captain Todd's BA-510. Their radio code names are Clipper and Speedbird.
Clipper 100, New York Center, squawk ident.
Clipper 100. Identing now.
100, Roger, radar contact.
Speedbird 510, squawk ident.
510 on contact, squawk ident.
Speedbird 510, radar contact. Speedbird 510, climb and maintain 4,000.
Clipper 100 cleared to flight level 240. We're leaving 4,000 feet now.
Clipper 100, Boston Center, maintain flight level 240.
From the New York Control Center, the plane is handed off to Boston Control.
510, flight level 260.
Speedbird 510, squawk ident.
Roger, Boston, squawk 1100. And squawk ident.
Roger, Speedbird 510, climbing and report reaching 260. I have you on radar contact. Roger, Clipper 100, climb and maintain flight level 330. Report passing 290 and reaching 330.
The collision risk here, where aircraft are under constant radar control, is influenced by the ability of the ground controller to operate under extreme pressures at the peak hours.
Roger, Clipper 100, understand. 133.6. Changing to Mountain Center, 133.6.
At Boston, the jets from John F. Kennedy International Airport are joined by transatlantic flights from other airports, adding to the tidal flow.
877, Roger.
From Boston, the jets are handed off again, this time to Moncton, New Brunswick, and finally to Gander in Newfoundland. Gander is Land's End and the end of radar control. Now Jim Waugh and Norman Todd are on their own. They must navigate with great care to stay in their assigned corridors. When they first started flying, there were no corridors. Going back to the days of the first transatlantic crossings, there were only 2 flights to London per week. Pilots of both flights flew the routes they wanted. It sometimes took as much as 20 minutes to get a simple radio message through. There was little risk of collision, even when storms blew them off course. Air navigation was less a matter of avoiding another plane than just reaching the destination, a feat which sometimes took as much as 18 hours. As the number of flights increased and the skies above the North Atlantic became crowded, the airspace was divided into east and westbound corridors. With little experience to go on, authorities arbitrarily decided that the corridors would be 120 miles wide. At this distance, there seemed to be little risk of mid-air collision. The main risks of transatlantic crossings were still mechanical failures. But as traffic continued to grow, the corridors could not handle the number of planes. So, in 1966, the width of the corridors was reduced from 120 miles to 90 miles. But the Pilots Association, representing the men whose lives were on the line week after week, protested that the narrower corridors increased the collision risk, so the corridors went back to 120 miles, which they are now. The need for airspace remains, and having raised the question of collision risk, it is now necessary to come to grips with it. The risk of collision between Captain Waugh's plane and Captain Todd's is determined by their ability to navigate. Captain Todd navigates with the Doppler system. It sends out 4 radar beams which strike the surface of the Earth and are reflected back to the plane. The change in pitch or frequency of these radar beams, caused by the motion of the plane, gives a measure of the speed with which the plane is moving over the ground, in a forward direction or sideways due to crosswinds. The Doppler system is linked to a magnetic compass, which is not always 100% accurate because of variations in the Earth's magnetic field and in the structure of the plane. There are 2 independent Doppler systems and fluxgate compasses on the plane, which average out most, but not all, of the errors. The advantage of the Doppler system is that it gives a continuous indication of position. Jim Waugh has been helping to test another system called inertial navigation, which also gives a constant position report. The heart of the inertial navigation system is a stable platform that is kept horizontal by 2 high-speed gyroscopes. A third gyro, shown beneath the platform, keeps the platform vertical. 2 sensing devices measure the slightest movement of the platform from the normal upright position. One, lined up with the airplane, measures forward speed. The other, at right angles, measures side-to-side movement caused by crosswinds. During the test, Captain Waugh's plane carried 2 inertial guidance platforms, again to average out the errors. As of now, Pan American has not decided to use the present system. Some transatlantic planes use other systems, such as celestial navigation, in which the navigator uses a sextant, similar to the ones that ship captains have used for centuries. He shoots the sun or other stars, and by means of a star table, a plotter, and a map, he determines the position of the plane at the time of the fix, which may be as much as 100 miles back, and establishes his present position and expected course from a projection of past positions. But the sun and the other stars are not always visible, and rapid shifts in wind can quickly introduce drift errors. Most planes use LORAN, some as a backup system, some as a primary. LORAN depends on distant radio stations for position information. By means of a pocket computer and dividers, the navigator can determine his position from point to point. But LORAN is subject to occasional radio interference, and its accuracy falls off sharply at these huge distances from the ground-based stations. Different navigation systems, operated by crews from dozens of different countries, with different degrees of accuracy and different kinds of position plotting, result in planes sliding far across their corridors, occasionally even into a neighboring corridor. It may be possible to avoid collisions at jet speed when the planes can see each other, but at night, or in low visibility, or in clouds, the lives of hundreds of people depend on the ability of each and every plane in the corridors to navigate accurately. But what is the exact degree of collision risk? To find out, U.S. Coast Guard cutters have recently been stationed in the North Atlantic beneath the air corridors. They have special radar systems to collect data on the actual flight paths of the transatlantic aircraft of all nations. the data collecting system is untouched by human hands. To avoid accidental human bias, each plane has a special code for radar identification. As the plane passes one of the Coast Guard ships, it's automatically questioned by a transmitter aboard the ship. The plane then automatically returns the signal and its position is plotted. This information is recorded on magnetic tape, which is then sent to the Royal Aircraft Establishment in Farnborough, England. The huge experimental station where much of Great Britain's aeronautical research is carried out. The data is analyzed by a group of scientists headed by Professor Kenneth Treweek.
We have, for some time, been developing methods for assessing the level of collision risk in air traffic systems. And we are now applying these methods to the evaluation of the risk in the North Atlantic. You might suppose, because there have been no collisions in the North Atlantic, that there is no risk. But this seems to me most unlikely, because the concept of complete safety is as unreal as perpetual motion. By looking at many thousands of radar observations of actual flying errors, we found just a few in which one aircraft had strayed out of its own airspace into the airspace allotted to the neighboring aircraft. These two aircraft are obviously exposed to risk of collision. The risk is very small because there's a lot of airspace, but we did find that the risk was nevertheless real. That made us keen to see if we could quantify it and decide how much risk there was. And then it would be possible to compare the measured level of risk with what could be considered to be a really safe standard. So we developed these mathematical techniques together with the mathematicians from other countries with a view to processing large quantities of radar data, data from navigators' logs, into a final result giving a statement of risk.
To explain these mathematical techniques, we asked Mr. Treweek and his associate, Peter Reach, to describe some of the complications involved in making this mathematical analysis of the flights across the North Atlantic.
I'd suggest we started with a very simple two-dimensional introduction to how these errors arise. Draw a little box around the track of our aircraft. And this little box is 2,000 feet high.
Little box is a big box.
2,000 feet high, maybe, say, 120 miles or 90 miles, depending what your lateral standard is going to be.
Sure.
The aircraft is traveling into the paper, and then we would indicate that the aeroplane is meandering about its track by drawing a little line like this, which, on rare occasions, may go outside that box.
Yeah.
And what the radar data will tell us is the proportion of time for which, on the average, all these flights are outside that safe box of air.
Let's put in the aircraft next door, shall we? Because we've got to consider its meandering about its desired path. And it's only when they meander so that they're overlapping that a collision can occur.
We now want to find what proportion of all the flying time is spent with this aircraft just exactly interfering with this one.
Yes.
And obviously, most of the time when this one strays into the box of the other, there will be no interference.
Yes.
But just on rare occasions, there will be, and that is a collision.
Yes.
And this sort of thing is so rare that we would reckon in a safe system to find only 10 seconds or so in 100 years, wouldn't we?
Yes.
Now, that, I think, is a point we have to get over as to how rare this is and how very careful we've got to be not to use the normal statistics of events which happen very frequently.
No matter how many observations we take in a reasonable time, from radar or navigator's logs or what have you, we never get enough to tell us exactly what the distribution is. If we stop long enough to, we took enough observations, the whole navigation system would change. This is the reason why one can't make precise estimates of risk. One can only set some sort of limit to the
Exactly, the high limit and the low limit with some confidence that we're in between.
Yes.
Now, having got a figure like, let us take 10 seconds in 100 years. This isn't exactly what it's going to turn out to be, I expect.
Yes.
But suppose we did. We still haven't got collision risk. Lots of people think that this is the collision risk, don't they? We have seen this said many times. But in fact, the 10 seconds when these aircraft are supposed to be actually flying through each other, if you could imagine them to be insubstantial aircraft at this stage, might represent one collision that took 10 seconds, or is it made up of 2 or 3 collisions lasting much less than 10 seconds? And in the simplest form, we just conceive of an aircraft, a pair of aircraft, about 300 feet in total extent, slowly passing through each other, typically at a rate of about 100 feet a second, 50 knots.
Yes.
So if we divide 100 feet a second into 300 feet, this is about 3 seconds, and we would say that 10 seconds is about 3 collisions.
Yes.
And now we've got 3 collisions in 100 years.
Perhaps the other most important factor of uncertainty is the effective collision size of an aircraft. If we could neglect the excrescences, the vortices shed behind the aircraft from near the wingtips, then it's quite a simple matter to take the collision dimensions as setting the dimensions of our collision slab. That's okay. But if we aren't able to neglect the vortices, or if the addition that they make to the effective collision size is uncertain, then it may be more efficient to use something like the Monte Carlo technique, in which in effect we treat the variables as rather complicated dice and get the computer to roll these 3 sets of dice time and again, perhaps 100,000 times, to give us a statistical average estimate of the risk, and in addition to that, the spread that we get about this average, so that we can use the spread to set a sort of confidence limit. That's how the output would be. The output would be a distribution of estimates of the collision risk. And the larger if you want more confidence in not having underestimated the risk, then you have to take a higher risk estimate.
This sort of systematic approach can show the safety for any set of separation standards. But the final choice as to whether to work to 120 miles or 90 miles falls on the authority responsible for aviation safety.
We estimate Shannon at 4-5. Clipper 100, roger. Cleared to climb to maintain 340. Shannon, upper green 1 to London.
Sandwich, speed at 510. Roger, 510 was 60 north, 30 west, 1918. Glide level 340. Estimating 59 north, 20 west, 1957. The wind 315, diagonal 60. Copy Canada.
Free descent check. 1,300 pounds. On.
A field approach check, please.
Right, flaps and slats selected. Speed brakes, check 0.
Yes, check 0.
Seatbelt sign on. Threshold speed 128, bug my side.
Bug this side.
Clipper 100 would like to restart our descent at 12.
Fin tank fuel.
0.
Engineer's approach check.
Completed.
The approach check is complete.
Clipper 100 passing flight level 250 and understand cleared now to 6,000 feet. Clipper 100.
Clipper 100, good evening. Report the outer marker. Runway 10 left. Surface wind is 360 at 7 knots.
Maintaining 2,000.
Clipper 100, roger, and you're clear to land. Surface wind 360 at 8 knots.
Down gear. There's a guy right in front of us, sir.
Out. Flat 40.
3 green. And the Clipper 100's established to wait right. You're about +5.
All right, check's okay.
+5. +5. +5.
Roger 100, landed 5-2, continue rolling, next green's on your right, and 121.90 when clear. 510, Roger, now clear to land, 010 at 8 knots.
And my throttles.
Your throttles.
300 feet, 400 feet a minute, 85%. 100 feet, 300 feet a minute, 83%. Spoilers, and reversal selected. Reverse power. Full reverse power you have. 100 knots.
Inboards to idle.
Inboards to idle. 80 knots.
Cancel.
An animated chart produced by a computer of a future day's traffic flow across the Atlantic underscores the problems faced by the aviation authorities. Scores of huge jets loaded with westbound travelers have climbed into the sky and settled down in their air corridors for the long journey across the ocean. Eastbound jets have rolled along the crowded taxiways of John F. Kennedy International Airport and climbed into their air corridors. Each dot represents a jet airliner, including supersonic transports. As a result of the cooperation of many countries, a rare event itself, pilots and passengers will soon know how much risk there actually is that any one of these planes will collide with another at the 120-mile and 90-mile separations. For the first time, scientists will have thought through the problem, collected accurate data, and come up with an objective result. Then it will be the job of the airlines, government aviation agencies, the pilots, and those of us who fly in the planes as passengers to decide which of these separation figures and their associated dangers we will agree to. Will we accept 3 collisions over the North Atlantic every 100 years? 6 collisions? 20? What will be our level of acceptable risk?